The Specair tutorial shows you how to fit a non-equilibrium spectrum. First, we import the raw experimental spectrum of a cold plasma discharge. The size of the plasma is unknown, so for the purposes of this example, we set it to 0.1 centimeters. To subtract the experimental offset in intensity, we select Find Minimum in the Data menu, which puts the horizontal marker at the lowest value, which is also displayed in the top right corner. Then we select Set Y Values and subtract 31.57. To make a copy of this adjusted spectrum for later, we select Duplicate Spectrum from the Tools menu. Before we start the fitting, we also import the measured slit function. While an approximate trapezoid often works for preliminary work, accurate fits need the proper slit function. It is also important to normalize it to get the right unit conversions. To start the fitting, we select Fine Transition in the Tools menu. Since we are working with a high-resolution spectrum, we adjust the option in the bottom left corner before pressing the Fine Transition button. The first suggestion by Specair is N2 second positive, which looks right, although there's an experimental offset in the wavelength. We select Update Settings. In the window, we see that Specair has selected the option to fix the electronic temperature at 10,000 Kelvin. This means that an equilibrium plasma does not emit any measurable radiation at the suggested temperature, which is 700 Kelvin in this case. Instead, the plasma had a high electronic temperature and was not in equilibrium, so this is the setting we need to generate spectra. We set the mole fraction to 0.78, which is the nitrogen fraction of air, and since there was an offset, we choose to optimize the temperature at a later stage. Now that a new spectra has been calculated, we can normalize it together with the experimental one. The wavelength offset is again visible, and to fix it, we zoom in on the peaks and find the wavelengths for both by placing the mouse cursor on the plot. We select both imported spectra and then choose Set X Values in the Data menu. The difference was 0.4 nanometer, so we add that. The overlap now looks much better, so we can go ahead and select Fit to Spectrum in the Tools menu. As the electronic temperature is much higher than the others, we fix this temperature before pressing Optimize. Specair performs several iterations to optimize the temperature, which turns out to be about 400 Kelvin. If we delete the old spectrum, we can see that the agreement with the experimental spectrum is excellent. We are only looking at a single vibrational band, so the vibrational and translational temperatures are degenerate. But we can find the electronic temperature by fitting the absolute magnitude of the spectrum. For this, we use the temperature loop option in the Tools menu, which allows us to calculate batches of spectra with different temperatures. We choose to vary the electronic temperature starting at 400 Kelvin with increments of 1000 Kelvin up to 9400 Kelvin. The remaining temperatures are set to 404 Kelvin, which is the value we got from the optimization. When we press OK, Specair calculates 10 spectra. Let's hide the highest temperature spectrum and zoom in. We see that the experimental spectrum falls between those at 8400 Kelvin and 7400 Kelvin. So let's delete the batch we calculated before repeating the procedure. Now we use a narrower range starting at 7500 Kelvin with increments of 50 degrees. This time, the experimental spectrum is in the middle of the batch, so let's zoom in to get a closer look. The experiment falls between the 7700 Kelvin spectrum in magenta and the 7650 Kelvin spectrum in green. For even better precision, we can repeat this one last time, starting by deleting the previous batch for clarity. This time, we use 5 Kelvin increments as we calculate the last 10 spectra. We can again zoom in and compare the spectra in different colors with the experiment. The best agreement seems to be the blue spectrum, which had an electronic temperature of 7680 Kelvin. Let's get rid of the last batch and calculate a spectrum with the best fit. The calculated spectrum agrees well with the experiment, and we have found that the electronic temperature was high at 7,680 Kelvin, whereas the rotational temperature was low at 400 Kelvin. For more information about Specair, please visit our website at SpectralFit.com.